Hello dear friends, today we are going to discuss semiconductor electronics, which is the important topic for your class 12th as well as for your higher physics. So in this lecture we will discuss what is semiconductor, why do we need semiconductor, band theory of solids and types of semiconductors, that is intrinsic and extrinsic semiconductor. We will discuss these types of semiconductor in details. So now let us have a brief discussion on what is semiconductor. So semiconductors are materials that have the conductivity between the conductors and the non-conductors. Means they have the conductivity between the conductors and insulators. So semiconductors may be elemental semiconductor. Here the word element signifies that it is made up of a single atom. For example, the silicon and the germanium. Now next come to the compound semiconductor. Here the word compound signifies that this semiconductor is made up of more than one atoms. For example, let us consider the inorganic semiconductors like CDS, GaAs, gallium arsenide, cadmium sulfide, and etc. There are also a lot of compound semiconductors like organic semiconductor, anthracene, and organic polymers like polypyrrole, polyaniline, etc. So now let's come to understand why do we need a semiconductor. So dear friends, we know that the devices which we use at our homes like mobile phones, tablets, smartphones and TVs, these have semiconductors. So for these devices, for these electronic devices, we need control flow of electron. So these semiconductors provide control flow of electron. So that's why we use these semiconductor materials in them. So your question should be, sir, is there any other material which also provide control flow of electron? So my answer is yes, there is a device, vacuum tube is its name. It also provide control flow of electron. So now your question should be, sir, if there is already a device like vacuum tubes, so why we need this semiconductor? So let's do a comparative analysis of the vacuum tubes and semiconductors based on different parameters. So if we see the size of the vacuum tubes, so it is very bulky, or you can say it is very large. But if you see the size of semiconductors, it is very small, like over like its size is like it can be seen in like chip everybody has seen. So you can assume it that. So if we talk about another criteria, that is power consumption, vacuum tubes is very high power, okay, and semiconductors takes low power. If we talk about the operating voltages, so vacuum tubes operate on very high voltage and semiconductors operate on low voltage. If we talk about the lifespan, so vacuum tubes have very limited lifespan and semiconductors have large lifespan. If we talk about the reliability, vacuum tubes are low reliable and semiconductors are high reliable. So in conclusion, we can say here both devices are following the same thing, but why we use semiconductor? Because it is more better than vacuum tubes in various parameters as we have seen. Okay, so now let us understand the band theory of solids. So now everybody have studied Bohr's theory in chemistry. Either you have studied in chemistry or you have studied in physics. So what is postulates is that the electrons move around the positively charged nucleus. That electrons move around the positively charged nucleus in circular orbits, and every electrons have definite energy levels. Okay, every cell have definite energy levels. So there is some similarity here, that inside the crystals each electron has the unique position. Okay, so these electrons have definite energy level because it will revolve around the nucleus in orbits, and every orbit have their energy levels. So the energy band, which includes the energy levels of the valence electron, So what is valence electron? The electrons in the outermost cell. So if we talk about this figure, here outermost cell is cell number 4, that is N cell. So the valence electron, the electron which lies in the 4th cell is the valence electron. So the energy band which includes the energy levels of the valence electron is called the valence band. And the band above this energy level means that if an atom has 4 cell and above that 4 cell, the energy levels are known as the conduction band. Okay, so if there is no external energy provided to the atom, so these atoms are in their specified circular orbits. Now let us discuss how the bands are formed. So here I have considered the case of the silicon. Silicon has atomic number 14, and it has 4 electrons in their orbit. Okay, say atomic number 14, so 4 electrons in their outer orbits, and this this 4 electrons are in the third orbit. Okay, so now here considering this, so this has a one energy level that here I specified. Okay, so suppose the here we are considering now only one atom. Okay, so this is the energy level corresponding to that particular one silicon atom. Okay, but in a crystal, what happens? In a crystal there are there are n atoms, means there are a large number of atoms. So every atoms have specified energy levels. So now every atoms have specified energy levels. So now let us consider this is the energy level of the first valence electron, first atom. This is the energy level of the second atom. This is the energy level of the third atoms. Likewise, there are n atoms. So this is the energy level of the n atoms. Okay. So these energy levels now starts to look like a band because they are very closely spaced. So they starts to look like a band. Okay. So this is how the band is formed. Okay. The upper the means the highest energy level in the valence band is known as the is represented as here EB, and the lowest energy level in the conduction band is represented here as EC. This is the in general I am talking about. This is the general case when there is no external energy is provided. Okay, so you should have a question that how semiconductors is different from the others like insulator and conductors. So here I have discussed that this is the diagram of the insulator, means here the gap between the valence band and the conduction band, which is known as the energy gap. This energy gap is very high in the case of the insulator, and this energy gap is in medium is in means it is less than 3 electron volt, you can say. It is in medium size, medium length in the case of the semiconductors. But in conductors, these bands like you can say valence band and conduction band overlap with each other. So now let's discuss about what is the types of semiconductors. Intrinsic semiconductors and extrinsic semiconductors. So intrinsic semiconductor is a pure semiconductor, means it is not doped. So you can say what is doping, what is dope. Dope means here that addition of impurity is known as doping, and the atoms which are doped are known as dopants, means which are added are known as dopants, and such a material is called as doped semiconductors. So now come to the extrinsic semiconductors. So what happens in intrinsic semiconductor, means in pure semiconductor, if you add a small amount of the impurity, then this type of semiconductor is known as extrinsic semiconductors. Okay, so you have a question that, sir, why we are adding impurities to the intrinsic semiconductors? So you must know the answer that If we add impurities to these semiconductors, the conductivity of these semiconductor is increased. Okay. Now let's have a discussion on the intrinsic semiconductors. What is, as we have already discussed, that intrinsic semiconductor is a pure semiconductor, and now we will discuss here by an example. Let's take the example of the silicon. So silicon atomic number is 14. It has the 4 electrons in the outermost cell, in the means in the n is equals to 3 cell. Okay, 3 number cell में. So 4 electrons. So here I have shown the configuration, that this is the silicon, and 1 2 3 and 4 electrons in the outermost cell. So now if we consider, since in a lattice or in a crystal there are n number of atoms, n means a large number of atoms. So here I have considered a large number of atoms. One silicon like this is a lattice structure. Okay, so every silicon have 4 atoms in its outermost cell. So let us consider this part. Okay, let's take me. Okay, let us consider this silicon. Okay, this one. So this has 4 electrons, this one, okay, and this one, consider this one and consider this one, and its surrounding silicon like this. It has also 4 electrons, this one, this one, this one, this one is for this one. So what happens here is, this silicon is covalently bonded to their surrounding atoms, like this is bonded to this is bonded to this is bonded to this is bonded to this. Okay, this electron correspond to this and this electron correspond to this. So here the silicons are covalently bonded. This is the condition when there is no external energy provided to the crystal. So suppose the external energy is provided to the crystal. Okay, then what happens? The electron will start jump. Okay, means the electrons will be excited. Let's see the case here. This is the case. The electron here gets energy, extra energy, and it started jumping to another energy levels. So electrons from here jump, and the space, the vacant space which the electrons leaves is known as hole. What is known as? It is the hole. And the electron which leaves, the its position is known as the free electron. Okay, what is it known? It is known as the free electron. So now your question should be, sir, what is the charge of this hole? So hole should be positively charged. And in the case of the intrinsic semiconductor, now you can understand from here that in the case of the intrinsic semiconductor, the number of electron is equal to number of holes. How? See, if one electron jumps from here, one hole will be created. Two electron jumps from here, two hole will be created. Likewise, so number of electron and number of holes are equal. Now next come to types of extrinsic semiconductor. Because you know the extrinsic semiconductors are impure semiconductor, means here doping is done. So doping is also done in two types: doping of the pentavalent atom, what doping of the pentavalent atom, and doping of the trivalent atom. The pentavalent atom have valency 5, means they have 5 electrons in their outermost cells. There are some examples here I have mentioned. And in trivalent atom there are 3 electrons in their outermost cell. Here I have mentioned some example also: indium, boron, aluminum, etc. Now let us discuss these by an example. So let's consider the first n-type semiconductor. So here I have taken the example of the phosphorus. Phosphorus is a pentavalent atom. Pentavalent atom means it has the 5 electrons in their outermost cell. Okay, so here outermost cell is 3, third cell. So it has 2s electron and 3p electrons. So 5 electrons in outermost shell. So pentavalent impurity it is. Okay. So here the electronic configuration is shown. The silicon have 4 and this phosphorus have 5 atoms in outermost shell. So now consider the doping. Okay. So phosphorus is doped here. Now silicon is an intrinsic semiconductor. So what happens? The electrons, like silicon has 4 electrons and it have 5 electrons. So 4 electrons will be covalently bonded. 4 electrons will be covalently bonded. 4 electrons will be covalently bonded. Okay. So what happens? There is one extra electron left. Why it is left? Because see, we have added the pentavalent atom. So the extra electron which left is, yeah, this one is extra electron. This one is left. So here this extra electron will make the free electron. Okay, and that's why the free electron moves, and that's why the conductivity of the semiconductor increases here. Okay, conductivity of the semiconductor increases by this way. So in this case you can see that the number of electrons is greater than the number of holes. Number of electrons is greater than the number of holes. Okay, number of electrons is greater than the number of holes. You can clearly see, because see, in pentavalent atom there is one extra electron, that is this, because four electrons are covalently bonded to this silicon, but there is one extra electron. So obviously there is one extra electron. Okay, so number of electron will increases. Now let's consider the case of the p-type semiconductor. So as we have already discussed that p-type semiconductors is uh, trivalent. Okay, trivalent atoms are doped here. So let us consider the case of the boron. Boron has electronic number atomic number 5, and it has 3 electrons in their outermost shell, 2 s electron and 2 p 1 p electron. Okay, so total 3 electrons. So what happens? See, here I have shown the electronic configuration. This one electron, this one, this one. Okay, these are the 3 outer electron of the boron, and silicon, as already discussed, it has 4 electron. So what happens? There is one extra vacancy. See, there is extra vacancy. Vacancy means hole, we have discussed. So if we dope it into the intrinsic semiconductor, if we dope boron into the intrinsic semiconductor, what will happen? See, these atoms are covalently bonded, covalently bonded, covalently bonded. But if you can see, the boron have one vacancy. Okay, since it has 3 electron in their outermost shell, this has one vacancy. So what happens? It will leave a hole. Hole means positively charged. Okay, so there the number of hole in, you can say, the in p-type semiconductor, number of hole is greater than number of electrons. Okay, this is the clear from this picture. Okay, now thank you, bye bye.